In particular, let's say that I had a more complicated system that looked something like this. I had A, and I had B, and I had C, and then well, let's throw in one more, D, and a register, right? And somehow I have found that the combinational logic over here is such that maybe this had a delay of 20 nanoseconds, this had a delay of, let's say, 5 nanoseconds, this had a delay of 10 nanoseconds, and this had a delay of 30 nanoseconds, right? I can ask a couple of different questions over here. What would the single cycle clock period be, right? And the answer to that is, let's say I have a clock edge coming on this register, my critical path then becomes going through all of these 4 different units, right? So that I end up with 20 plus 5, 25, 35, 65 nanoseconds, okay? Now, can I pipeline this? Well, assuming that each of these units is in time invariant and so on, yes, it is possible to pipeline, right? Again, keep in mind that the only reason we can pipeline is because we don't have any feedback paths. If we did, then we would not be, pipelining is possible in certain restricted ways, but it's not straightforward. So in general, we are not going to consider things where we have feedback paths, right? The question then becomes, where should I pipeline? What is the best that I can do by pipelining, right? And if you look carefully at this, you will realize that there is this block D over here. Well, the best case scenario that I might want to hope for is Ts divided by, let's say, 4, right? Because after all, if I could insert 3 of these and break them up all into separate units, could I get down to Ts by 4, right, by breaking it up into 4 stages? And the answer is no, I can't do that. Why is that? Because I know that I have this block D, which when I say 30 nanoseconds, the assumption is you are not allowed to break it any further. You don't know what's inside D, you don't know how it's implemented, you don't know what gates it's made of, you are not allowed to modify it in any way. If that's the case, then D remains as it is, right? And if I then ask you, okay, now what's the best that you can do, the story slightly changes, right? I'm no longer going to try and break it into so many different stages. What I could do instead is to try and say, okay, maybe I could go and put in a pipeline register here and maybe a pipeline register here, right? In which case my pipeline critical path becomes either 20 nanoseconds or 5 plus 10 nanoseconds as it passes through B and C, or 30 nanoseconds. And when I have a system with various different paths of different lengths, how do I find out which is the worst case? Well, take the maximum among all of those, right, which turns out in this case to be 30 nanoseconds. So the best pipelined clock period that I can get for this system is actually going to be 30 nanoseconds. Now it's interesting, what actually ends up happening over here is, if I now feed in one input over here, it takes one clock cycle, another clock cycle, and a third clock cycle in order to get out of this, which means that the latency in this case of the pipelined system is going to be 3 times Tp, which is equal to 90 nanoseconds, right? But because it's pipelined and as soon as I have passed through the first stage, I can now feed in the second data, what I'll get is that the throughput is going to be 1 over Tp, or 1 over 30 nanoseconds, as opposed to the single cycle system where the latency is basically the same as the clock period. It's 65 nanoseconds, which actually turns out to be better than the latency of the pipelined system. But the throughput is equal to 1 over 65 nanoseconds, which is less than half of what it was in the case of the pipeline system. So the pipeline system has a much better throughput, right, more than double of the single cycle system, but it has a worse latency, right. The point is latency is very often less of a concern, because as you can see from this picture over here, the latency is just a one shot thing, right. The first value that I get has a certain delay associated with it, but subsequent values start coming fast, right. And this is literally the main sort of motivating idea behind all pipelines, whether they be in manufacturing, in cars, or in a food assembly line, or anything else that you can think of. The core idea of why we even consider pipelining is precisely this. It may even slightly increase the latency for generating your first output, but from that point onwards you can get a significant throughput. In other words, you can get a high rate at which data gets processed and comes out. Okay. So as you can see over here, pipelining can be done in general, especially when you have systems which basically consist of a large amount of combinational logic that is basically passing through between a pair of registers. As I said, there are restrictions on when pipelining can be applied. In particular, if you have a feedback path where data is coming back from one of the combinational units into a previous flip-flop or a register, pipelining has to be applied with a lot of care, right. That's not something that we are going to get into. The conditions under which pipelining can be applied is not something that we are going to discuss further over here, right. But as you can see, the main metrics that we would be interested in would be the latency versus the throughput. And in general, when we talk about speed, we are finally probably interested in throughput. Now, everything that we have actually discussed over here, right, all of this in terms of what is the number of pipeline stages, as you saw from this example, adding just 2 registers and basically breaking it into 3 pipeline stages was the right thing to do. I could have added one more register out here, right, and made it 4 pipeline stages, but my clock period would still have been bottlenecked by this 30 nanoseconds, the longest path over there. All that would have happened is my latency would have become even worse. It would have gone to 4 into 30, which is 120 nanoseconds, without improving my throughput at all. Okay. So deciding where exactly to put these registers in such a way that your paths get balanced and broken up into the right number of stages is something that is fairly straightforward to do, but requires a little bit of thought, right. So the number of pipeline stages and how you balance those different stages will have an impact on the latency as well as the throughput that you can achieve from a pipeline. Now clearly, when we are adding pipelines registers over here, we are adding extra hardware, so it's not that it's coming completely for free, right. The more registers you add over here, they do have an impact on the area. It's not just on the area, right. Remember that I neglected the TCQ and the T setup of all the registers to start with. What happens after a while as you pipeline, especially very high performance systems, is that you start seeing that your TCQ and T setup start becoming similar in value to the actual delay through the combinational logic. At that point, you have hit essentially what would be called diminishing returns, right, because any further breaking down of the combinational logic is wasted because your TCQ and T setup are going to be the bottleneck as far as your critical path is concerned, and adding more registers is actually just adding area without really getting much benefit in terms of performance. And well, in this case at least, for a simple sort of data path based system as we have shown over here, there are really no control signals that need to get added. So, but on the other hand, there can be scenarios where the kind of logic that we have over here has a little bit of extra control signals also that determine when the pipelined execution can happen, when I should not allow a particular kind of execution to happen, and so on, right. Where does that happen? In the context of a CPU, right. This is not something that I will be getting into in much detail over here, except to sort of just briefly mention that all the stages that we talked about while discussing a single cycle CPU, right, which basically starts off with fetching an instruction from memory, decoding it, which basically means pulling out the correct set of register values that are required for your ALU to execute, sending it to the ALU for execution, assuming that it's an ALU operation, right? Or if it was not an ALU operation, then basically fetching data from memory if it is load, or sending data to memory if it's a store, right? And finally a write back, which basically occurs in either ALU or load type operations, where I get some data and I need to put it back into the set of registers, right? All of these can be thought of as different pieces of combinational logic. We have already seen that in a single cycle execution, we would start off with fetching data from an instruction memory, passing through a combinational read through the registers, going through execution. There would be no memory if it was an ALU operation, but then I would write back into the registers that I already have, right? All of this basically happens as one continuous set of operations or combinational logic, right? But if you look carefully at it, these can be broken down into separate computational blocks, and it turns out that we can actually insert the pipeline registers exactly over here, right? This entire understanding of how exactly this happens and how it gets implemented is a little bit beyond the scope of what we can do in this course, but is very much a subject of the course on computer organization, right, which would sort of look into this part of it in a little bit more detail. So when you do have something like a 5-stage pipeline CPU, which is the most common, at least the way that it is taught, right, but not necessarily the most common in terms of how it is implemented, right, it turns out you are doing exactly the same thing. You basically come up with a path through the your logic that has a long critical path, and then try to break that down into smaller portions in such a way that you can put these pipeline registers between blocks and take a pause basically before going on to the next stage of computation. One more thing that you might notice is this looks as though it actually has a feedback, and I just said that you can't do pipelining when you have feedback. As I said, that's part of what gets complicated over here, right? It is one of those things that you need to look deeper into the implementation of the CPU in order to fully understand how it can be done and how pipelining over here is actually a valid thing to do, right? So pipelining is extensively applied in the design of modern CPUs. And the basic idea of pipelining is exactly what we discussed earlier, right? You take a single cycle CPU, break it into stages. Usually things like fetching the instruction memory or the data memory, executing inside the ALU, those are the most critical operations. Although you can have some critical paths associated with possibly fetching data out of registers or possibly even writing back into the final register, right? You could implement something like a 3-stage pipeline or a 6-stage pipeline. There have been pipelines up to around 20 stages in length, but at that point it turns out that you start hitting something called hazards, and hazards are essentially things that come up when certain operations have dependencies on other operations that went ahead of them, right? And because they are waiting for some data that needs to be generated by one of the previous operations, the whole pipeline has to sort of stop and wait until the data is ready. Once again, these are things that would be discussed in more detail in computer organization or a course on computer architecture, right? At this point, I'm just sort of mentioning them as interesting sort of further ideas that come up when you take these optimizations to their natural conclusion. This is just a picture of what a CPU pipeline diagram typically looks like. It is very similar to what we saw in the trivial case, right? You might remember this picture out here, right? I had a stage 1 and an output. Essentially what I am saying is each of the stages is performing a different part of the computation. In the same way, this diagram is also showing the same thing. It's sort of saying that we have different instructions that are sort of passing through the system, each of which has to pass through different sort of computational stages, right? I first need to fetch the instruction, I need to decode it, meaning that I need to pull data out of the registers, I need to actually perform an ALU computation, If it's something like an add, I don't really have a mem operation, but because my pipeline cannot sort of change things around dynamically, I just sort of skip one cycle over here and say, okay, fine, if there was memory, I would have done it here. Right now, I don't really do anything. Pass it on to the write back, and this is where it actually gets written into a register. The next operation is some other kind of a subtract, which also goes through fetch. The good thing is, the moment the add fetch was completed and it handed over data to the decode, it can go and fetch the next instruction, which is a subtract. The same hardware that fetched the add instruction also fetches the subtract instruction. In the third cycle, it fetches the load instruction. In the fourth cycle, it fetches a store instruction, and so on, right? So the point is that you have these different units of hardware that are sitting available in your system, right? And the question is, what can you do with them, and how do you make use of them and keep all of them busy as far as possible, right? So to sort of wrap up this whole discussion of pipelining, the core idea of why pipelining is used in the first place is you have certain amount of hardware, and it is possible to sort of try and split operations across these different stages, right, such that the different units of hardware are being kept busy as much as possible, right, and you balance out the different stages in such a way that the time required to pass through any one of them remains more or less equal to passing through any other stage, right. In that way, you can sort of try and keep all the hardware units busy to a large amount of the time, and thereby get a high throughput without necessarily sacrificing much in terms of extra hardware or logic.